Hello everyone, and welcome to the November webinar presentation by the Underground Construction Association Young Members Group. My name is Anthony Bauer, and I am one of 3 members of the UCA of SME Standing Committee for the UCA Young Members. I am the chair, and I'm joined by Aaron Clark, the Professional Development Chair, and Shannon Goff, the University Outreach Chair. As the holidays are rapidly approaching, this will be our final webinar of 2015, and we will restart with our regular schedule on the last Wednesday in January. Keep an eye out for an email regarding January's presenter or visit our website. Today we continue the webinar series with a presentation by Carol Ravano on avalanche and drainage mitigation of the BNSF Snowshed number 7 in Glacier National Park. Carol Ravano has 21 years of geotechnical and civil engineering experience and is the company-wide manager of the McMillen Jacobs Associates Railroad Engineering and CM Group. Ms. Ravano specializes in management of construction projects for railroads, state, county, city agencies, and private owners, geotechnical site investigations and analyses, and construction monitoring. Ms. Ravano has designed landside stabilization and railroad geotechnical and tunnel rehabilitation projects, many of which have been performed under live track conditions. She has performed construction monitoring, ensuring procedures, materials, and structures meet contractual specifications, safety requirements, and environmental regulations. Carol, thank you very much for presenting to us today, and when you're ready, you can share your screen.
Thank you. Sometimes the technology is a bit much. Anyway, I want to thank Younger Member Forum for having me. Allow me to present this to you. I know it's not quite what many of you think you might be doing, but as my career shows, you never know where you're going to end up. You got my my educational background. I went to UC Berkeley, got my undergraduate degree way long ago in 1983, and the economy was terrible at that point, so my professor said, why don't you stay and get your master's? So I did that in geotechnical engineering, and I'm glad I did so. I always loved the idea of being a geotechnical engineer was really a favorite of mine, just because it combined being able to be outside and working on interesting projects, and that's what it's really proven to be. I'm going to just give you a quick rundown of my job experience. You never end up where you think you're going to end up. I first worked at a very big, now extinct engineering firm called International Engineering Corporation, which became Morrison Knudsen Engineers, and it's gone. And then having married someone in the Navy, I ended up in Seattle and worked for Dames & Moore, one of the first geotech firms up here. That was for 9 months. Got laid off, went and worked for Golder Associates, where one of my favorite jobs was working on the new Mount St. Helens, at that point, Mount St. Helens Roadway and Visitor Center. Then my husband got transferred to Italy. So while there, I worked for the Navy for a year, and then we moved back to Seattle. I worked for the Navy some more, and then I took 10 years off, and we can talk about that later, but that was quite a career shift. Raised 2 boys, and then after 10 years came back, and I've been back working for 13 years. Worked for a small firm. This is leading up how I got into tunneling. Worked for a very small firm who actually did a lot of railroad work. And next thing I know, I was in so many railroad tunnels, I couldn't imagine it. I'd actually taken railroad classes, or excuse me, tunneling classes at UC Berkeley from Tor Brecky, who's now deceased, but awesome, very inspiring tunnel engineer, and thought I'd never get into underground work, and that's where I spend most of my time now. So anyway, this project is near Glacier National Park, and we're now McMillen Jacobs Associates, but at the time we were Jacobs Associates, and we performed the site recon, the design, help with the bidding process, and resident engineering during construction of this. Last year at AREMA, which is the American Railway and Engineering Maintenance of Way Association, a big railroad conference, we presented this paper. The design work on this was done between June and October 2012, and the construction took place between August and October 2013. Just so you have an idea of the location, this is the state of Montana. And you can see where Glacier National Park is, up there in the upper left corner. And our job is right on the very southern boundary of Glacier National Park. The orange line is the piece of the BNSF railway that goes through there, called the High Line Subdivision. And it's a very scenic, remote area, if anybody's ever traveled through there. It's also a highly used rail line. 40 freight trains a day and 2 Amtrak trains go through, moving 1.5 million cars every year. Amtrak also moves 17,000 passengers to this point, to points and also within Glacier National Park. Along this route, there are multiple avalanche chutes that drain large watersheds above the tracks. Snow avalanches have damaged the structures and trains along this route for years. This, right now, the BNSF owns and maintains 9 of the original 12 snowshed structures that were constructed between 1912 and 1927 by the Great Northern Railroad, the predecessor to the BNSF in that area. Originally, the drainage through these snowsheds was with hand-dug ditches, and that's the runoff from Glacier National Park. Very sensitive ecological area, and because of the park's environmental restrictions, we couldn't repair these drainage ditches. So we had to come up with an innovative drainage design that we could capture the flow of the surface runoff, yet allow avalanches to pass over the snowsheds unimpeded. I just threw in a few pictures to show you how picturesque the area is. Again, starting out my career, I never thought I'd be clinging to the side of mountains in Montana, but you never know where your jobs are going to lead you. So this is just, every once in a while I go to these job sites and think, I am so lucky to have this job. This is actually a picture of this snowshed. This is snowshed 7 that had the drainage problems. And you can see to the left is the incredibly steep slope. That's where the water and the avalanches would come from. And because the drainage was blocked, the original drainage, the water was flowing over the top of the snowshed, taking out the maintenance road below and causing damage inside the snowshed. Snowsheds Act, I always call it a tunnel, but it is a snowshed, but we have a lot of the same restrictions when we work here. This is an example of the typical snowshed. It's a double track, and it consists of a roof made by 12-inch by 12-inch creosoted timbers, and they're supported by 16-inch by 16-inch timber columns. And then there's a reinforced retaining wall on the uphill side. Reinforced concrete counterfort wall design, 30 feet high, 15 feet deep, and a 2-foot thick wall. The fill behind the wall consists of soil, boulders, and miscellaneous uncompacted construction debris, meaning we don't know what they put down there. The top of the fill forms a flat surface extending from the roof, extending approximately 80 feet wide between the back of the retaining wall and the toe of the slope. That toe of the slope is the boundary for Glacier National Park. And so when we were thinking about how we do this design, that was a really critical, one of the critical elements. Here we go. This is an avalanche in 1979, and where you can see the avalanche flow, that's the east end of Snowshed 7, where we needed to work on. Avalanches have historically damaged the railways traversing the watershed chutes in this canyon just east of Essex, Montana. So this is between East and West Glacier, Montana. To protect the railway, the snowsheds have been constructed to divert the avalanches over the track structure. While they're great withstanding the avalanches, they weren't designed to accommodate the surface flow that was actually damaging them. Here's a photo of the bigger picture here, and you can see our drainage basin, watersheds. We've got the West Basin, the East Basin, and the Main Basin. And the red dotted line down below is Glacier National Park boundary, and you can see where our snowshed is located. Highway 2 is just to the south of the snowshed and the rail line. To facilitate the design of the pipes, we retained geoengineers to perform a hydrological and hydraulic basin study of the watersheds above snowshed 7. The study included estimates of the peak flow rates for various design storms, culvert pipe capacity recommendations, and estimated maximum thrust in pipe at the peak flow. Geoengineers also provided assistance in the design of erosion control elements and avalanche mitigation measures. Using a 100-year, 24-hour flood event, the findings from the study indicated that our peak flow was going to be 300 CFS, maximum flow velocity up to 17 feet per second, and the total thrust at a culvert pipe elbow, which we'll show you later, is 10.5 kips. So here's a little bit of the drainage problem that we had. On the left, you can see what you're looking at is actually the lower portion of that slide is the top of the snowshed roof, and you can see the water just flowing over the top. And then the photo on the right, you can see where the water is coming down over the edge of it. And the problem is here it wears out the access road. And the BNSF had tried to put sheet metal strips on top of the snowshed roof to divert the water runoff, but it really didn't help that much. So the resulting water leakage fouled the ballast beneath the tracks. And then the pumping action of the trains going over this jeopardized the integrity of the track structure. You can see that in the photo on the left. And then the water flowing over the top routinely washed away the embankment and access road. So on the left, you can see where the water in the track structure makes it worse. They had a slow order. That's what they call when they have to slow the trains down through this area. It's a double track, highly trafficked area, and they don't like to have slow orders on them. And then you can see on the photo on the right how it's damaged the sidewall of that retaining wall. And due to freeze-thaw action, then you get a lot of spalling. You can see the rebar in there and general damage. Here's a close-up of some of the structural damage, probably caused by freeze-thaw, also by probably excessive loading on the back side of the wall. So when we were coming up with a design, we wanted to mitigate all of these problems. Here's a close-up. Somebody had put a crack gauge on there, and it was showing not only cracking outwards, but downwards also. So some of the interesting design criteria, constraints that we wanted to take in. It's a very remote site. Gosh, from the closest Whitefish, Montana, decent town, Kalispell, it's probably an hour and a half. So we had to think about that when we concrete or any materials like that. It's adjacent to the national park, as I already said, meaning they did not want us to touch at all anything on their property. We actually put up a barbed wire fence to remind the construction workers that we weren't supposed to touch it. Very constrained site. We have the mountains, to our back, and we've got the snowshed below us. We have the highway. We have, creeks and rivers. Very limited laydown area. One of the other things we wanted to do is try to use as much native material on site that we could. And we were pretty lucky in that. I'll go into that a little bit more later. But we were able to use the native rock and soil, which helped with costs, but also schedule. And a very short construction season. Snow doesn't melt up there until, July often. And it starts up again in October, November. So we didn't have much time to actually do the work. Here's what we came up with. We had about 7-8 months to do the design and do all our calculations, etc. But basically, we had the surface runoff coming from the watersheds uphill, of Snowshed 7, and discharging behind the snowshed retaining wall. Here's a cross section. You can see our snowshed to the right, the kind of a cutaway of the retaining wall back of that. And then what we designed. So we've got a catchment basin to intercept, collect, and direct the surface runoff towards a centrally located drop box and culvert system. The berm and the catchment basin, which we've identified as the berm catchment area, occupy the accumulation zone of an avalanche path. So to counter the potential ramming forces during an avalanche, the berm has a relatively low profile and few surfaces normal to the avalanche flow. To reinforce the berm, a high-strength techo mesh was anchored on top of the riprap and on the foreslope of the berm using spike plates attached to tension 14-foot-long grouted soil nails. I'm going to show you pictures of each of these, but this is for the overall. The steel mesh is designed to prevent the riprap beneath from becoming dislodged from scour and avalanche events. The array of soil nails also anchors the berm structure against thrusts from an avalanche. We put heavy-duty steel pipes up on top, 3 of them, 3-foot diameter. They captured the surface flow and conveyed the surface water over the snowshed and into the existing creek below. It was critical that the pipes were large enough to handle the peak flows and robust enough to survive the impact of periodic avalanches. Also, extra sturdy pipes would negate the need for structural support of the over 30-foot-long pipe span from the top of the snowshed to the thrust block below. So we chose half-inch thick steel pipes. They were lined parallel to the expected flow of the avalanches, such as the debris would slide by the pipes unimpeded. Based on the criteria established during hydraulic modeling, we decided to use 3-foot diameter pipes instead of one single larger pipe due to the additional cost for shipping, handling, and installation. The 3 smaller pipes outweigh the benefits of just using one pipe. At the base, before it hits the corrugated pipe to the stream, we had to construct a 5-foot by 5-foot by 15-foot steel fiber-reinforced concrete thrust block to account for the concentrated load and thrust created during the pipe if it was full flood conditions. The splash pipe was buried, the block was buried to provide passive thrust resistance. At the end of the outfall culverts, we designed a riprap mattress to absorb energy, dissipate flow, and minimize the erosion into the existing creek. So here's our start of construction. Now, as I said, this is a really remote site. So we had to pioneer a road to get the materials up over the side of the snowshed to the back of it. We had a couple choices, pioneering the road into it or lifting the materials up and over with a crane to the back of the site, and we chose the pioneer accessing road. We used a couple of cat excavators, one with a rock hammer and another with a cubic yard bucket, and took the material out and stockpiled it, excuse me, which helped with the schedule. So I showed you the cracks inside the, excuse me, on the back of the retaining wall of the snowshed. And we wanted to not only fix some of those cracks, but we wanted to, because of the surcharge loads from the equipment during construction and the additional overburden from the earthen berm that we were putting on top of this that would affect this retaining structure, we added self-drilling rock anchors, 2-inch diameter, 25-foot long, Williams self-drilling. We put 34 of them in, located about 8 feet from the top of the, below the top of the retaining wall, spaced 10 feet apart. They were self-drilling and used grout instead of water for drilling fluid because the ground conditions behind the retaining structure were varied. We really didn't even know what they were, but we knew that they would probably cave. So having the grout instead of the water helped us just kind of get the grout out there, and then we didn't, and the self-drilling, we didn't have to excavate a hole, pull the rods out, put a rod in, because they probably would have caved in. So this was the quickest way to solve the problem. We also had, you can see the cracks, that's the side wall, the access road that I showed you coming up to the right of it, but we added some reinforcements there to take care of those cracks that you can see. So this is on top. You can see the snowshed roof in the photo on the left, and clearing and grubbing. Again, you can see the steep slope off to the left, and in addition just to doing the clearing and grubbing, we dug some test pits to locate suitable material for the berm construction. We had some lab samples done, and it showed that there was some well-graded material with low permeability that we could use for the berm structure. We also needed rock for armoring, and wandering around the site with a geologic hammer, we were able to find some good sources for that also. So that saved a lot of time and money and helped with the schedule. So here's just construction day in and day out. We not only did the design, but we had a resident engineer out there during construction, because given the unknowns with what we were going to encounter up there during construction, we needed somebody out there to make decisions and for all sorts of things, from what type of materials to use, et cetera, et cetera. So typical lovely day out there. And here we are over excavating and proof rolling. Again, not knowing what material was there, we wanted to make sure that we had decent compaction of the native material before we started to build on it. And here's the, again, we designed the berm up on top behind the snowshed to intercept, collect, and direct the surface runoff towards a centrally located drop box and culvert system. Again, we had to design it to withstand the potential for avalanche flow. So this material was the native material, and we put it in 12-inch lifts and compacted it with a vibratory roller to 95% of standard Proctor. Pretty typical. We also placed a filter fabric beneath the riprap armor to segregate them. And then it was time then to start moving the pipes in place. Again, 3-foot diameter. I think these sticks are approximately 30 feet long. 1/2-inch thick steel wall. So pretty hefty. Extra sturdy, and this is coming up that access road that we pioneered. You can see the double-track railroad to the right. This work was, at times we call it performed under live track, meaning there's trains running here. And so in order to move equipment or personnel across, we either have to have a window where they don't allow trains, or and we always have a flagger, someone from the railroad offering us protection, telling us when the trains will come, et cetera. So it's, in that sense, different than a normal construction site, but we were lucky to have no problems at all. So here we are getting the first sections strapped to the snowshed roof. They're sitting on saddles, pressure-treated 6x12-inch timbers, and then strapped down. Those were attached to the roof, of course, and then they're strapped down with 3/8-inch by 4-inch stainless steel straps. Here's the elbow portions down the front. You can see bolted down pipe before they're being connected. So this is part of a tricky part, actually. And the thrust block is going to go down there at that elbow down below. What I want to say is also in the background you can see where our drainage basin is. So it's very high, very steep, rugged country, and that is Glacier National Park. At the base of the pipes, we had corrugated culvert connecting which would then ultimately be buried. These then went into a rip-wrapped outfall and connected to the existing creek where the water was going to anyway, but this is a much more controlled manner. You can see the three short stubby, those are going to be manholes in that location for clean out if necessary. Here's a thrust block that was poured after the culvert pipe was buried. Again, 5 feet by 5 feet by 15 feet. It's steel fiber reinforced concrete. There is no rebar in that. So this is down at the base. And then up top, we have our berms. You can see those out to the side. This is the culvert intake, and this is the form. So this is formed concrete. They did get concrete trucks in. They said they had to drive about an hour and a half, so it had to be specially formulated so it wouldn't set up. Anyway, this was all formed on site. First the base slab, and then the wing walls and the head walls. So integrated into the pipes that went over the top. And here's the finished structure. Again, to the left, you can see the berm. You can see the geofabric there separating the fine-grained berm from the riprap on top of it. And then I'll show you on top of that, we're going to put our techo mesh. So around the sides of this culvert intake also, then they backfilled with the finer grained sandy soil and compacted that. Here's somebody doing with a hand tamper. So, and then we have our techo mesh, which is a very sturdy reinforced wire mesh. And they put it in with, it was put there to reinforce the earth berm against the lateral avalanche thrust as it was designed. So you can see them installing these anchors. You see, those are 14-foot long anchors that they're putting in there, not only for the techo mesh, but also then to reinforce the actual berm. And here's a close-up of the plate. I don't know if most of you aren't familiar with a techo mesh or a similar type, but the plate that you see there to the right of the intake structure, those actually, they have prongs that set in into the mesh and really hold this thing down. So it's not just thrown on there, it's actually tensioned into place. You can see around the edge of the culvert intake structure, the wire that connects the edge of it, cable I should say, not just wire. It's very heavy duty. So but it's a great product for uses like this. And then you can see the trash rack installed to keep the debris out of the culvert. That was done in place. Anyway, so this is kind of the final, what our upstream look like. And we just thought it would be waiting for snow melt to do the job. Anyway, and here's, again, the completed structure. So this is facing into Glacier National Park with the pipes coming over. Most everything's buried, like a lot of our underground work. All our hard work, nobody gets to actually see, but we know it's down there and feel proud about it. Anyway, so there'd been the avalanche in '79. That had been the most recent one. We completed this project in October of 2013, and lo and behold, the next March, less than 6 months after we finished construction, another avalanche came through. And as you can see in the photo, we couldn't see what our work had done. We actually, it was probably about a month before we knew if it had worked as designed, and we're happy to say that it did. But you can see the avalanche path, just like it was in '79, completely buried. That front face of that snow shed is at least 30 feet high, so that's quite a high. I mean, that snow there was probably 40 feet high at that point. So was a happy day when we heard that the pipes were intact and there had no real visible damage. I went back to the site in May, and you can see up to the edge of the snow shed in the front, this is the snow and debris and big trees that had come down from the avalanche over the top of the snow shed. But it was great to see them, see everything working. This is like I think there's about a 12-inch diameter tree that was just snapped off. It's amazing to see the power. And this is then up on top a little bit later because everything's dry, but these are just some of the smaller debris that was left up there. There was other stuff that the railroad did move out of the way of our grate there. So it's functioning as designed. The berm was intact. That Checo mesh did its trick. And then the intake on the left, but then the outflow. So we could see that the drainage was functioning even before we could see the complete pipe. So quite proud of the job that we did there. And then that's the end of it. This was, here's my contact information if anybody has any questions, wants to contact me. But let's see, I was going to give the conclusion. I don't know if there's going to be questions, but they said at the end if I wanted to, let's see, talk anything about my passion for the industry. And I have to say that for the most part, we do a lot of railroad work, but we also, I spend most of my time in railroad tunnels around the United States. We've done a lot of capacity improvements, et cetera. And then a lot of the tunnels are just over 100 years old and just need upkeep and especially drainage issues. But they asked if I wanted to, let's see, overcoming career challenges. And I'm not sure what stage some of you are. Some of you might be students and then some early on in your career, since this is the Younger Member Forum. But probably for me, the biggest challenge was getting married and moving with my spouse. And as I said, I used to joke that my resume would, I should put on microfiche, and some of you probably know what microfiche is, but I'd worked 9 months here and a year here, and that's what you get for marrying somebody who's in the United States Navy. But what I found was, because I had a really good education and tried to keep up with what was going on, that if you've got a great education, take advantage of that, and you're going to land. You're going to land a good job. Anyway, that is challenging, but it gave me flexibility. So, and then advice for young engineers, and I guess probably one of the main things is network. Go out and meet people at the Younger Member Forums, at the conferences and conventions and things like that, because it is kind of a small group, especially people working in underground, even in geotech, and you're going to work for somebody or know somebody who works for somebody, et cetera, et cetera. So don't be afraid to go out and network and meet people, and be active in your Younger Member Forum or in your professional society. So, okay.
Carol, this is Heather from SME. I just want to thank you for that great presentation. Sounds like you guys overcame some big challenges there, especially with the location.
Yes, it was incredibly challenging because you're, 2 hours away really from concrete, and goodness gracious, if it's not like you can forget something, So a lot of planning. The other thing, lots of communication between us, between the contractor, between the railroad. That's critical, especially when you're in remote sites. I think it's critical all the time, and no matter where you're working, to be able to communicate with each other, written and orally, but planning ahead, having a good schedule. And I think a lot of times too, we're site constrained here, but since you guys are underground construction, that's kind of always a problem. There's never enough laydown area and things like that. So.
Sure. Well, let's get started with some questions that have come in during your presentation. The first question came in from Zane. Zane wanted to know, why was the peak flow 100-year, 24 hours selected as opposed to another?
You know what, Zane? That's an awesome question. And if I were, you know, we had geoengineers do that, and I'm embarrassed to say, I don't really know. I guess it was because we wanted to design, I mean, a realistic design, yet not overpowering. So the other thing is, this structure is already 100 years old. The railroad doesn't like to go back and, you know, redo things every few years. So they want to build it to last another 100 years. So I think that's why we chose that flow.
Great, thank you. The next question reads, approximately what percentage of the total project costs were related to site access and site preparation?
Oh, goodness. See, these are all awesome. And I wish I could point to my colleagues to say, you know, our MOB fees we usually figure are about 10% of our total cost. So in a site like this, we actually use 10%. Probably if we had an urban site and we're doing the same, or rather closer to, you know, and we might go a little bit closer to 5%. But when we're dealing with this remote part, we're going to say that would be about 10%. The other thing that comes into play on these jobs is, and not so much when we're working on top of the structure, but when we're working inside, you saw us putting the rock bolts inside, is we have short track windows, work windows that we can work in, and that adds some cost to projects. Probably it increases maybe about 5 to 10%, because instead of having an 8-hour or 12-hour shift, we might get promised a 4-hour window or a 6-hour window or an 8-hour window. So it takes a special contractor to be able to adapt to that. There you can see we weren't very far where we could clear the track and get out if a train had to come by. But in other places, you know, we can't do that. So you have to get in, you have to do your work, you have to clear your area because trains are going to be running. So you can't leave anything, you can't leave your structure in an unsafe situation because trains, perhaps with people on them, are going to be coming through. So that itself adds some cost to the project.
I bet you've got to be quite flexible to deal with all of that.
You do, and I've worked with numerous contractors that are awesome at it. They're used to it, but we've had others that aren't and don't take advantage of shorter windows or something like that. So that can add a lot of time and money to their budget and stretch out a schedule, unfortunately. So.
Great, thank you. The next question reads, do you see a lot of tunnel rehabilitation work coming in the future due to the relative age of railway tunnels in the U.S.?
That sounds like someone just planted that just for me. Actually, yes, we do. We're working on, right now I've probably got 5 or 6 different railroad tunnel rehabilitation projects going on. Not only, like I said, most tunnels were built either late 1800s or early 1900s in the United States, and they're holding up really quite well. They might have been originally timber sets and now have been converted to a concrete lining, both for structural and also vandalism reasons. What happens a lot is what you saw there was freeze-thaw going on from leaky tunnels. A tunnel acts like a gigantic drain, so all the groundwater just loves to come pouring towards the tunnel. And depending on how it's constructed, what the ground it was constructed in, you often have drainage problems. So right now, the big focus in 3 of the tunnels I'm working on, we're doing the design for, is drainage. And how do we mitigate it? Some have invert struts in them, which act as little mini dams. Invert struts are concrete members that go from one sidewall of the tunnel to the other sidewall in the tunnel to help act, the forces that are acting in on the tunnel sidewalls. And so we're in one tunnel where those act as little mini dams. keep the water from flowing out of the tunnel as it's meant to, and then just the whole invert with the track, et cetera, just is terrible. Again, they have to do slow orders through them. So there's a lot of work to be done, and it takes really clever ideas of how can we rehabilitate this tunnel given short track windows, given where we're located, et cetera, et cetera. We do a lot of icing shields in tunnels. That's a big problem, again, for both safety for trains. Sometimes ice builds up in a tunnel such that it goes up and over the tracks, and it can actually cause derailments. The other thing we do a lot of with lines that have been converted that are no longer active rail lines is we do a lot of rails to trails. So turning old rail lines into bike or pedestrian paths, and that's pretty popular. We have quite a few here in Washington State. But, and again, that's, rehabilitating the tunnels. A lot of people are afraid of working in tunnels, but it's been really interesting to be able to go and rehab those and get those open to the public again, or whatever the case may be. We're working on a few right now. So, but the other thing that we've done, and there's some work still to be done, but as a company, we've helped active rail lines, the class ones in the United States, Norfolk Southern, CSX back east, Union Pacific Railroad, Burlington Northern, Santa Fe, is make them into double stack tunnels. I don't know how many of you are familiar seeing trains go by with the containers on them, and it used to be that they would put one container on a train and it would go, and then they realized, hey, we could put two on top of each other, and yes, of course we have a little more locomotive power, but we can expedite the moving of stuff. So, and that's great when you're out in the open, but once you hit a tunnel, you can imagine if they're not designed, and a few railroads try to double stack their own tunnels, and with not very good consequences. But what you need to do is you need to make that square peg fit into the round hole, so to speak. Some tunnels are naturally big enough, or were designed, they weren't necessarily designed big enough because it's a newer concept, but we had to go through a lot of tunnels, hundreds, 200 or 300 tunnels, and make them, for capacity improvement, notch out or cut out the tops of the tunnels, and that's really tricky engineering work. Working with structural engineers, you have to do your, figure out seismically also. So it's really challenging engineering stuff that you're going to see in your new tunnels in underground construction, different types of modeling, et cetera. And then again, working remote locations, short work windows, et cetera. So I think there's enough tunnel work still to come in the United States. So.
That's great, Carol. Thank you so much for presenting today. We'd like to remind all of our attendees that today's session was recorded, and within 48 hours we'll have the video available on the UCA Young Members website. Everyone who's registered for today's presentation will receive an email notifying you when that video is ready. Carol, would you like to make any closing statements today?
No, I'm just so thank you for asking me to do this. Shannon actually asked me and then left the country. But anyway, you guys were so professional, and I'm so excited that people are interested in the underground industry. I think it really is a place where things are really growing. With I see it, less environmental issues that you have to deal with. And anyway, good luck.
Thanks again, Carol. We're getting some attendees texting in thank yous. So everybody, we hope to see you again for our next UCA Young Members webinar presentation in January, and have a great afternoon.
Thanks.